Welcome to the next video in the Measure Theoretic Probability series. And in this video, I want to give a brief history of measure and integration. Now, this is another motivation sort of video like the previous one, but the previous one was focused on motivate using measure theory in probability theory. This video in this history, I want to kind of give motivation and explanation for just measure theory. Because, of course, when measure theory was originally developed, it wasn't developed with applications in probability in mind. And so I, at least personally, find it very sort of enlightening or whatever. It helps me to understand why we make the choices that we make in measure theory, to understand what problems historically people were facing and how these choices solve those problems. So it may come as perhaps a little bit of a surprise that you could really trace the origins of measure theory and integration theory back to Fourier series. By the way, just in case this is worth noting, when I say integration theory, that doesn't mean just any integral. Integrals, had been somewhat understood since about the time of Newton and formalized by Riemann and so on. So when we talk about integration theory, we're not so much thinking about the Riemann integral as we are the Lebesgue integral and integrating these somewhat more exotic general things. So anyway, measure and integration theory kind of gets its start from Fourier series. And really, when you look at the history of mathematics, it's kind of astonishing how many things that don't seem like they have anything to do with Fourier series really do have their origin from looking at Fourier series. So anyway, in order to talk about this, let's recall the formula for the coefficients of a Fourier series. I'm not even going to really depend on that much knowledge of Fourier series, and I'm not even going to write down the Fourier series, because the real challenge is in computing the coefficients. And so here's the formula for the coefficients. That's all we're really going to talk about. Now, it may be a little obvious that this integral can, for certain choices of f, be quite hard to compute. And so one way to deal with that difficulty is to look for a Taylor expansion for the integrand. And this is, in some challenging situations, actually possible. And when we do, the hope is that by replacing the integrand with the equivalent Taylor series, this power series, we could then integrate the function term by term. That is to say, we could swap around the integral and the sum and merely integrate x to the n, which we know how to do perfectly well. And notice I'm dropping indices, and I'm also dropping sort of like bounds of integration and so on, because I feel like they just kind of clutter the picture, and we don't need to be worried about those details. So now you might think, why is this a problem, right? So isn't the problem solved? We just switch the order of integration and sum, and we're done. And certainly if the sum were finite, then we know by the linearity of integration that that would be absolutely correct. There is nothing to worry about. However, when the sum is infinite, we have no such guarantee. And if you write out the sum as this limit of partial series, then you can kind of see that really the issue is swapping the integral and the limit. And there's very little reason to think that that should necessarily always be possible. So to talk briefly about some history of the people involved, what did the mathematicians at the time of, investigating these things have to say about all of this? Well, Fourier himself seemed to swap the integral and sum, and therefore also that limit, without really worrying about the validity of it. He probably, just guessing about how lots of mathematicians thought and felt at the time. He probably just thought that it was intuitive and it got results nicely. So it should be correct, right? Is probably what he was thinking. Anyway, but some mathematicians were worried that, it was during this time of increasing rigor in mathematics. And some mathematicians found that they could actually come up with examples where they could clearly demonstrate that the swap was invalid, that if you took integral of a sum, they could actually compute it, and then they would take the sum of the integral, and they could actually compute that end as well and show that actually they came out to be different. So then in cases where you can't compute one of them, how do you know that they come out equal? So that became a true concern for these mathematicians. And that inaugurated a period of research in which they hunted for conditions that they could put on this function f that would guarantee the validity of the swap. And that research program had some amount of success, but the victories were hard fought. And there's two senses in which that's true. For one thing, the proofs were long and complicated, taking up, mathematicians' lives when they're not producing other results. So that's not great. If that could be avoided, it would be great if we could just sort of make more easy and rapid progress. For another thing, the victories were small. For all that work, the theorems that we could produce were, in a sense, weak because the conditions that they had to place on the integrand f were so strong that not enough functions met those conditions, especially ones that came up in applications. And Fourier series have tons and tons of applications, so it is really quite important for the scientific project that we do this right, that we have the power to do this analysis on as many functions as we can possibly get. And so if we're missing some, that's a bad thing. And they definitely were missing some. So it was in this context that Lebesgue had an idea about how to approach the entire research project in a possibly more productive way. Turned out to be correct. He thought maybe we could actually change the very concept of the integral. Not extremely so, because we still want it to represent the area under the curve, but he realized that we could formalize that notion in a slightly different way. And let's now look at what that is. Now, before actually looking at Lebesgue integration, let's just rehearse the more familiar Riemann integration. And on the right-hand side of the slide here, I'm going to depict a very sort of brief representation of that for the function x squared on the interval from -2 to 2. And I'm going to just pick some evenly spaced partitions of the interval. So starting at -2 and going over to -1, I draw these rectangles with the height determined by the left endpoint, right? The point doesn't really matter all that much, but just for kind of uniformity, I'm gonna choose left endpoints. Why not? And so what we do, right, so we partition the interval, we pick some point within each cell of the partition, we use the height of the function, could call that the image of the function, and we have a rectangle width due to the cell, and we have a rectangle height due to the image, and we get a rectangle. And we do this for each of the cells of the partition. When we're done, we have a bunch of rectangles. We sum the rectangle areas to get a single approximation to the integral. And then we take the limit of all of the approximations as the number of partition points goes to infinity. So there's the Riemann integral, presumably completely familiar. Now let's see how the Lebesgue integral is different. Really, the only real way that it's different is that we go from the image back to the pre-image. So in the Lebesgue integral, we will partition the range And so again, right, I'm going to use the same function x squared, and we're going to look at the interval from -2 to 2. So we might as well restrict our range to 0 to 4. I'll use the partition of the range, which has points at 0, 1, 2, and 4. Our arbitrary choice. So let's just look at one approximation due to that partition. Now, on each cell of the partition, I'm going to compute a pre-image, right? Not an image this time. We're going backwards, so to speak. And we're going from the image back to the pre-image. Now, I'm going to take the entire interval on the y-axis, compute its entire pre-image. And in a sense, that's because I need the entire region of the x-axis, which maps into this interval to get me a width of a rectangle. And in this first one, right, on the, when the y interval, so to speak, is from 0 to 1, then when I compute the pre-image, we can see that that comes out equal to -1 to 1. That's the interval -1 to 1 on the x-axis. And that actually forms a rectangle, a regular rectangle, just as we have it in the Riemann case. And we get a rectangle area corresponding to that. Okay, great. Now let's move on to the interval that runs from 1 to 2. And if we compute its pre-image, notice that we don't want the portion. Well, okay, so when we compute the pre-image, you can sort of take the point 2 on the y-axis and run a horizontal line to the left until you hit the graph of the function. This is just a sort of convenient way to just figure out what the pre-image is. And so you can kind of tell that that's going to hit it where the x coordinate is -√2. I draw a vertical line straight down to the axis, and we get this green rectangle on the left-hand side. On the right-hand side, we kind of do it all over again. And this is a sense in which you don't really get rectangles when you do Lebesgue integration. Okay, it's a collection of rectangles, and that doesn't seem so bad because, even in the Riemann case where you have collections of rectangles. But there's an important sense in which this isn't a rectangle, and that kind of matters. We'll talk a bit more about it in a minute. But so let's call this green collection of rectangles a pseudo-rectangle. I don't think that's standard language, but it's just, I think, evocative and helpful. So when something is not a rectangle, but a union of disjoint rectangles, we'll call it a pseudo-rectangle. So anyway, you get the pseudo-rectangle. It has an area, and we can compute that. And that'll contribute to the approximation of the Lebesgue integral. Then we do it all over again for the interval from 2 to 4. And we get, again, rectangle on the left, rectangle on the right. Together they make a pseudo-rectangle, has an area. We sum together all of these areas. That is a single approximation of the Lebesgue integral. And then there is some sense in which we take the limit of the approximations as the number of partition points goes to infinity. More on that all quite a lot later, but I just wanted to give this rough intuition for how Lebesgue integration contrasts with Riemann integration. Now, I just want to do a little bit more calculation based on what we said so far. So in this slide, you're really just going to, sort of see some more notation and writing on all the same calculations. So we see the pre-images of the cells of the partition as you see them here. And we can just use the interval widths to determine these widths, and then you add them to, right, if there's a disjoint union of interval widths, then you sum those together to get the pseudo width, so to speak. But I do want to indicate right here that there can be a problem, right? When this is a finite sum, there's no issue. And in fact, when you have these finite collection of pseudo rectangles and pseudo widths, in fact, everything is completely equivalent to the Riemann integral, and there's just no difference at all, really. The problem is that they're not always finite, that you can come up with certain, so to speak, nice functions that are continuous, differentiable, and so on. And yet, the number of pseudo rectangles that come from this process is infinite. And then the analysis is not quite so easy and obvious. And this is also really the sorts of cases where the Riemann and Lebesgue integral diverge. And and it will turn out, we'll see quite a lot later, that the Lebesgue integral offers in some cases like this, a significant improvement over the Riemann integral. But even though all of that is in some sense true, what it does kind of make us realize is that in order to compute, right, when we have these infinite collections of pseudo rectangles, we need some way of assigning them an area. And really, it's not the rectangles that's the problem, because the vertical dimension of the rectangles is not an issue. It's just a single interval always, so presented here. Really, the issue is the pseudo width, right? The pseudo width could be these crazy, who knows how many of them there are. It could be an infinity of these like intervals. And for all we know, possibly they're not even decomposable as unions of intervals, for all we know. It's a little hard to imagine what that would look like, but at least at first glance, we can't rule out that possibility. And yet, in every case, it seems like we want to be able to assign to this collection of real numbers on the x-axis its measure. So if we sort of state what we seem to want here, we would like to be able to take any subset of the real numbers and assign it a measure in some intuitive sense of what that measure is. Such that, like, for instance, if you were to give me an interval, then its measure would be the interval, right? So that's one intuitive notion of what we want out of this, so to speak, measure of subsets of real numbers. And we'd like to be able to do it for any subset of real numbers. And so our heroes in the story have been Fourier and Lebesgue, and along comes the villain Vitali to show to us that, in fact, this is not possible. And we'll see the proof of that in the next video. Of course, Vitali is no villain. He's actually a hero, because knowing that this is impossible has been a great help to us all, but it's just fun to be silly like that.